All right, so picking it up again here, we're now going to describe how we can find copies of particular real matrices or complex matrices which capture the matrix algebra of, say, complex matrices or quaternionic matrices. So in particular, we're trying to find a bridge between the world of complexes and reals and quaternions and reals, and quaternions and complex. So here's how it goes. So first of all, we can build this map from n by n complex matrices to 2n by 2n real matrices of a very special type as follows. So to start with, the row 1 map trades this complex number for this 2 by 2 matrix. So here the multiplication of 2 by 2 matrices mimics, in fact encodes the matrix, the multiplication of complex numbers. There's something in here that behaves like the imaginary number I, right? 0, 1, minus 1, 0. That matrix has, I think it's worth interrupting the flow of this for just a second here. For example, 0, 1, minus 1, excuse me, this is equal to minus 1, 0, 0, minus 1, which is equal to minus 1, 0, 0, 1. Of course, this is the identity matrix, and so this matrix behaves like I in the 2 by 2 real matrices. All right, now, if you had a bigger complex matrix, like a 2 by 2 complex matrix, then what you do is you just take each complex number and you swap it out for the corresponding 2 by 2 real matrix, all right? And you can see how you would define, more generally, you just do it element by element to construct this block matrix formed by these 2 by 2 blocks, all right? And so that's the natural correspondence between n by n complex matrices and n by n and 2n by 2n real matrices. They have a name. The image under row n of the n by n complex matrices is called the complex linear matrices in 2n by 2n real matrices. All right, now, so there's some very nice properties for this row n map. It is, it's a linear map with respect to the real vector space structure. Both of these, it's additive. You can pull real scalars out. But here's the kicker. It is a homomorphism from the multiplication of complex matrices to the corresponding multiplication of larger real matrices. And that's why this row n map is interesting, because it gives you this homomorphism like that. And in fact, it's it's an isomorphism onto that set. So, well, it's in the sense of algebras. It also preserves the multiplication and the addition. Now, there's also a nice correspondence between what it means for a mapping to be, complex linear. Now, I said this is complex linear. Okay, so this being complex linear means that it is in the image of the row n map, right? So this is complex linear if and only if the function induced from it in this way is a C-linear transformation. Let's look at the diagram here. Now here the Fn is the natural correspondence between Cn and R2n, which is just formed from stringing out the real and the imaginary parts like so. All right, so here's the diagram. So we're given this map. We're trying to construct the purple map. So what we do is we trade our Cn for R2n by just stringing out the real and imaginary parts. Then you multiply this 2n tuple of real numbers by b, by the right it's a row vector, okay. So you multiply on the right by b. That gives you another 2n tuple of real numbers, and then you convert it back to a complex vector by the inverse of the real imaginary string out map. And it follows then that in fact that G is complex linear, and the matrix of G in fact of course is it's an n by n complex matrix. So, but anyway, we have this. It's really nice though, because this means that the matrices which correspond to this complex linear matrix in 2n by 2n are naturally corresponding to the corresponding complex linear transformations on Cn in the natural way. Now, if you studied complex analysis with me, you have already seen this talked about in the case of the complexes as it relates to R2, where we learned that this correspondence is essentially the Cauchy-Riemann equations. More on that for another day. But there, of course, is this so-called, standard complex structure of R2n. I already wrote it down in blue on the other what are these? Other page, I suppose. J2n is the image of I times the identity under the row n map. That gives you the copy of what is behaving as I in M2n R. In other words, this gives you a 2n by 2n real matrix which behaves like the imaginary unit. So, for example, here's I in 2 by 2 real matrices. This is the quote-unquote I in 4 by 4 real matrices. You square this thing, so you get back to the minus identity. Yeah. By the way, you can write it in terms of the tensor product here. I should probably spend a little bit more time thinking about how I can restate things we've written here in terms of tensor products, particularly the Kronecker product. But oh well, leave that as a project for another day here. The standard complex structure again on R2n again is J2n. So, proposition. You might want to characterize when is it that a given 2n by 2n real matrix is complex linear, right? And there's a simple prescription. If it commutes, all right, with the standard complex structure, if it commutes with that, then that makes it for sure in the complex linear matrices. So this is just a real 2n by 2n matrix condition if it just commutes with this particular 2n by 2n matrix called the standard complex structure. So that's a neat little proposition, which of course is useful if you're studying a specific problem. You can see page 27 for the diagrammatic beautiful argument. Now, that brings us to quaternions. So quaternions, first of all, we'll view as complex, and complex elements of twice the size, and then as real elements of a larger size still. So one quaternion corresponds to 2 complex numbers, corresponds to 4 real numbers, all right? And the similar story plays out for matrices of quaternions. So here's the correspondence between MNH and M2NC. This is the map. A plus BI plus CJ plus DK is A plus BI, A minus BI, C plus DI, minus C plus DI. Now this map is motivated by a certain bit of algebra, which is, I think, on the next page. So I'm going to, here's the other thing we need, of course, beyond this definition of the correspondence between the quaternion and this 2 by 2 complex, we also need a way to swap out an n tuple of quaternions for a 2n tuple of complexes. That comes from rewriting this in terms of the usual relation on the so-called versors, ij and k. So like ij is equal to k, jk is equal to I, ki is equal to j. So I can rewrite this if I am so seeing it. Here's how to do that. So a plus bi plus jc, and then so I can swap out the k for minus j times I, right? And so then what I have is I've got, this is like one complex, this is like another, right? And so I can think of this as like z1 plus j times w2, where these are 2 complex numbers. And so I think of any quaternion as having the form z plus jw, where z and w are complex numbers, and then the pair is just z comma w. That's the correspondence. That's the G1. And likewise for Hn, you just repeat this over and over again. All right, well, yeah. let me just take a pause here for a second to show you some specific examples of these maps, because it's easy to get lost, and they're really simple. They're just, just takes a second to absorb what they're doing. First of all, the simplest case, 3 plus 2i, that gives us this 2 by 2 complex matrix, 3, 2, minus 2, 3. That's the definition of row 1. Then for a 2 by 2 complex matrix, I'll keep it pretty simple. Only one is genuinely complex. That's pure imaginary. That's pure real, right? Then you just do this in each thing. So like I goes to 0, 1, minus 1, 0. We talked about that. 3 goes to 3, 0, 0, 3. 0 goes to the 2 by 2 0 matrix in R, and this maps to that as we were just talking about. So we're swapping out a 2 by 2 complex matrix for a 4 by 4 real matrix, right? Which is quote-unquote complex linear, right? In other words, it induces a complex linear map of the corresponding copy of, in this case, 2 tuples of complex numbers with respect to that diagram we talked about before in the real imaginary stringing out map, the FN. Likewise, another 2 examples here. Example 3 for, let's see here, psi 1 of that quaternion, 4 plus I plus 2j plus 3k, we just, I'm following the formula I wrote on the other page, but basically I have the real component here, and then plus the coefficient, which is 1, I minus the coefficient, which one, so it's like a plus bi, a minus bi, this is c plus di, this is minus c plus di in the language of the other page. And so just following the numbers, right, 2, 3 goes here and here, that puts a minus 2 here, puts a 3 here, that's just the definition of the map. As you can see, we traded one quaternion for a 2 by 2 matrix of complexes. And then you can trade, and you can go one step further. You can say, well, I am going to go, and I don't like a 2 by 2 complex matrix, I want a 4 by 4 real matrix that shares all of the same algebraic features. So I'm like, okay, great, well, here you go, feed that to the row 2 map. That swaps out this 2 by 2 complex matrix for this 4 by 4 real matrix. This 4 by 4 real matrix algebraically behaves the same as this quaternion, as this matrix. So, but here the difference is the algebra here is the multiplication of quaternions, the algebra here is the 2 by 2 matrix multiplication of complex matrices, the algebra here is the 4 by 4 matrix multiplication of real matrices. Now, an algebraist would say, why are you saying the same thing 3 times? After all, these are isomorphic images. But the point is we have different representations in different spaces, and while they do share the same algebraic traits, they of course are, as point sets, rather different objects. This, for example, is where I would prefer to do real analysis, because it's, well, real. All right. But that's not to say that this or that don't have their purpose. I mean, that is the simplest presentation, right? You can't beat that. Look at that. I mean, that's simple. It's a number here. It's a 2 by 2 matrix, 4 by 4 matrix, right? So familiarity breeds contempt. Yeah, it's very familiar, but it's also very ugly. Less familiar, slightly prettier. Probably the least familiar to most students, and by far the most beautiful. Anyway, is good notation good math? I don't know, but here's another example. So I'm a glutton for punishment, so I decided to do a 2 by 2 quaternionic matrix. So here you go. Here you have it: 1 plus I, j plus k, 3, 4 plus k. So that, by definition, is you do the psi 1 map component-wise, just like we did before for the complex case. That gives us this 4 by 4 complex matrix. In other words, this is a quaternionic linear 2 by 2 complex matrix. All right, or you could say that this is just a quaternionic linear matrix in the complex 4 by 4 matrices. Words. Now, of course, I'm not content there. I want the corresponding real matrix. So we feed that beast into row 4. Row 4 swaps out 4 by 4 complex matrices for corresponding 8 by 8 real matrices. And there you have it, folks. This is the corresponding 8 by 8 real matrix corresponding to this 2 by 2 quaternionic matrix corresponding to this 4 by 4 complex matrix. Man, I love this stuff. Anyway, You can do calculus over all this stuff, but that's not in this book. That's for another day. I mean, he does have the Lie group structure and so forth later, as we'll get to. So again, just to recap, psi n of the n by n H matrix is a subset of 2n complex matrices. These are the quaternionic complex linear matrices. And then rho 2n of psi n of MNH is a subset of M. 2n is 2n right there? Yeah, I just used R. I used rho 4, didn't I? Yes, I did. I just looked at this for n equals to 2. So I had psi 2, but I had rho 4, and out popped 4 times 2, which was 8 by 8 real matrices. Again, the quaternionic real matrices of 4n by 4n size. The following are equivalent. All right, so we want to, this is going to be that sort of analogous to that condition we had about the commutation relation between the standard complex structure and the, the characterization of being complex linear in the real matrices. So here I would expect that it's going to be quaternionic linear. A matrix is quaternionic linear if it commutes with the representations of the versors, the I, J, and K for the quaternions. Let's see how it goes. All right. I promise I haven't looked ahead. So we need that B. Oh, it doesn't matter about K. Just I and J is enough. Of course, because I and J give you K. But so B is quaternionic linear, meaning that what that means is that through the correct choice of diagram, this 4n by 4n real matrix generates a corresponding left quaternionic linear map on the copy of Hn to Hn. All right. It commutes with the standard complex structures, if you will, although maybe abusive language here, I4n and J4n, which are just the images of I and J to the set of 4n by 4n real matrices. And of course, so B quaternionic linear doesn't mean what I said it means. That actually just means it's in the image. This defines, to say, part 1 is just to say that B is in this image. Part 3, I was describing what this image means in terms of mappings. It means that the corresponding induced map on Hn to Hn is H linear with respect to the natural string out the real and imaginary parts and reformulate your quaternion as a pair of complex numbers mapping. So it's also neat and tidy. This is really, really nice work. I have struggled through this with students, just doing hand-to-hand combat without the hand-to-hand combat with these things without the benefit of these mappings. And while it's of course doable, this is so much prettier. Anyway, so again, here's what those look like for I4. It's this and J4 is that. We actually saw that in my example page previously. Finally, the determinant. Determinant's a little funny. The determinant, you take the determinant and compose it with psi n. That gives you a mapping from the n by n quaternion matrices to the complexes. That's how to give determinant for the quaternion matrix. The determinant of A is just that. And the determinant for the complex is defined in the usual way. The thing about the quaternions is the order of order of multiplication matters, and the theory of the determinant is, at least a lot of the standard formulas are based on numbers commuting, which is fine for the complexes, but not for here. So to avoid reinventing the whole theory of determinants over a non-commutative ring, this is a convenient trick, I think. Anyway, I think there's other things you could do with the determinant than what's done here, but it is at least a solution if it's not the only solution. And with respect to this definition of determinant, it is the case that the general linear group over the quaternions is in fact a non-zero determinant. So this is a nice definition despite its apparent ad hocness. Is ad hocness a word? I don't know. Anyway, apparently the determinant of A is real, actually, for A in the quaternions, which is kind of weird because, on the other hand, the determinant of B is complex for B in the complexes. So it just so happens that with respect to this definition, it makes the determinant of a quaternion real, which is, that's kind of cool. All right. Anyway, so that's all I have for this bit. And the next little lecture, or talk, whatever you want to call it, we'll be talking about inner products on these things. Thanks. I'll start again here in a second.